Hello students. So today we'll discuss about non-linear wave shaping and so let's start. So what is mean by non-linear wave shaping? See, the circuits for which the outputs are non-sinusoidal. So for the sinusoidal inputs means you are applying sinusoidal inputs for the circuits and you are getting a non-sinusoidal outputs. Then such circuits are called non-linear wave shaping circuits, and we are having two types of non-linear wave shaping circuits: clipping circuits and clamping circuits. Why it is called actually non-linear means the elements which have been used in the circuit for doing this wave shaping are actually non-linear elements. So that's why the name non-linear wave shaping came into picture. Now, so non-linear wave shaping circuits are classified as I already said, so clipping circuits and clamping circuits. Now, what is this clipping circuit and what are these clamping circuits? Let's see in detail. So, non-linear wave shaping clipper. So, clipping means cutting and removing a part of the signal. So, if you see the clipping circuit is a circuit which removes the undesired part of the waveform and transmits only the desired part of the signal, which might be above or below the reference, some particular reference level. For example, so if you are having a sine signal or a square signal, so if you this circuit clipping circuit is actually used to remove the undesired part. If you want to remove some part of the signal like this, so you can do that by giving some reference level and you can transmit only the signal up to which is actually desired, and you can remove the undesired part of the signal as you can see in this graph. So a clipping circuit is a circuit which removes the undesired part of the waveform and transmit only the desired part of the signal, and which is above or below some particular reference level. Here reference level should be given, it might be 0 or something. So depending on the reference level itself, it actually clips the signal. Now clipping circuits are classified as, so since these clipping circuits are used to remove some part of the signal, these clipping circuits are also called as voltage limiters, means it is actually limiting the voltage by removing some part of the signal, or current limiters, and it is also, these circuits are also called as amplitude selectors, since these are selecting only the desired amplitude to be passed, and these are also called as amplitude slicers, means it is slicing the output waveforms. So this is called actually clipping and clipping circuits, and we are having two types of clipper circuits again here: single level clippers and two level clippers. So what are these single level clippers and two level clippers means? So if you are transmitting a sine signal like this, and at the output side, so only you are getting the negative part only, or you are getting only positive part and negative part has been getting clipped in this way, in this signal. Here positive part is actually getting clipped. So these type of clippers, clipping is nothing but a single level clipping, means it is either clipping a positive level or it is clipping a negative level. But there are other clipper circuits which can do both, which means at the output side you can find positive part as well as the negative part being clipped off. So the circuits which are used to clip at two different independent levels, such circuits are called as two level clippers here. So single level clippers means which clips either positive level or negative level of the signal. Two level clippers means it clips both a positive as well as a negative levels of the signal. And single level clippers again may be series diode clippers with and without reference, or shunt diode clippers with and without reference. Means these single level clippers can be designed using diodes. So those diodes, if they are in series with the input signal, they are called as a series diode clippers, and if they are in shunt with the input signal, they are called as a shunt diode clippers. And both with and without reference, these circuits can do clipping. And we are also having a clipping circuits which also use transistors also. Now let's see in detail about how this clipper circuit works with some examples. And talking about clamper, unlike this clipper, so these clamping circuits are actually changing the DC level of the signal. So these clampers here are also called as actually DC restorers. So why? Because so if for this signal, if the DC level is actually 0, so for in positive clamping, you are going to observe the output signal being clamped either in a positive or in a negative. Means it is actually changing the DC levels. So that's why these circuits are also called as DC restorers or DC reinserters, and different names are given. Just understand the definition here. Clamping may be two types. It might be a negative clamping with and without reference, or positive clampers with and without reference. So if you observe here, so negative clampers are also called as positive peak clampers. So why? Because so the second figure actually it is a negative clamping, means the waveform has been clamped towards a negative direction, and these negative clampers are called as positive peak clampers. Why? Because the positive peak of the signal has been clamped to the negative side. Means since you are clamping this positive peak, these are called positive peak clampers. Similarly, so this one negative peak clampers. So these positive clampers, this is actually positive clamping which is clamping above the reference level. So here this negative peak has been clamped towards the positive direction. That's why these are called negative peak clampers. Means you are clamping the negative peak in this particular operation. So clamping circuits are classified as two: negative clampers with and without reference, and positive clampers with and without reference. Now let us see diode clippers. So before going to the actual circuit, let's understand the operation of a diode actually. So VI characteristics of a practical diode is actually shown in this figure. So this is all we all know, and we have done experiments also on this. So these are the VI characteristics in both forward bias and in reverse bias direction, and we are so approximating this in terms of idealizing the diode. So here we are taking this figure B, C, D, E shows the VI characteristics of ideal diode. Means ideal diode means which is having a zero threshold voltage V gamma. So like as you see here, the threshold voltage of so diode is given as 0, means immediately by giving the input signal the diode will conduct it, and this same diode is getting approximated so by a curve called piecewise linear and continuous conditions, so like shown in figures C, D and E. So here we need to understand the concept that when this diode is actually in forward bias and when this diode is in reverse bias. So based on understanding and identifying the condition of diode, whether the diode is on or off, so based on identifying this, we can easily figure out what type of a clipping is going to happen and which part of the signal is going to be clipped and how the output waveform will look like. And the threshold voltage breakpoint for germanium material diodes are 0.2 volts, and for silicon made diodes it is a 0.6 volts. Means these are the threshold values for germanium and silicon. in diode clippers, as I already said, so series clippers are there as well as the shunt clippers are there. So first we'll discuss the shunt clippers and then we'll discuss about series clippers. So shunt clippers. So first we'll discuss a circuit which actually clips the output signal above the, so clips the input signal above the reference level. So let's see the circuit. And so this is the circuit, so which is having a resistor R, diode D and a reference voltage VR. So actually, so this circuit will actually clip the input signal applied so above the given reference level VR. So let us see how this actually works. So as I already said, we need to understand when the diode actually turns on and when the diode actually turns off. For example, if consider, so this is the input signal, so what we have applied, and this signal is applied at the input of this circuit, and there is some reference level. I am taking this reference level, so at this instant starting from 0, and let us say this is actually, so the peak value is 5 volts. Now what's happening here, see, when this diode actually turns on means, so when the input voltage is actually greater than this VR, means the voltage at this point, if this is greater than this VR, then the diode comes into forward bias. And what happens when the diode conducts, it actually works as a short circuit. And when this actually works as a short circuit, the output voltage what you see will be only VR. Means when the input signal Vi, means when this input signal goes above Vi, above VR, what happens? So the diode turns on, the output will be fixed at VR level. And what happens when this diode actually turns off? Let us see. If the input signal is less than this reference level, means like this, from 0 to VR, this is less than VR actually. So when this diode, when the input signal is so less than, when input signal voltage is less than, so this reference voltage, if this point is less than the input less than the reference voltage, what happens? So this diode will be in off state, means it works like a open circuit. Now when it is open circuit and there is no connection between this reference voltage and the diode and the entire voltage, so input voltage will appear across the output voltage. Like when Vi is less than VR, you will find the entire input signal getting passed at the output side. So means here this positive peak means the signal above the reference level is actually being clipped off. So that's why the name clipping above reference level is given for this circuit. Now let us see how these conditions again elaborately, so with the help of diagrams. When Vi is less than VR, means when the input signal is less than this reference voltage, what happens? Diode will be turned off, and you can see the equivalent circuit, it will be in this fashion. If the diode is in off condition, what happens to the output, Nana? So V0, the entire input will be appearing at the output side. Why? Because there is no connection between this VR and the circuit right now. So the entire output, the entire input signal appears so at the output side in this fashion. So now V0 becomes what? So Vi. So similarly, what happens for Vi greater than VR? If the input signal is greater than, if this input signal is greater than the reference voltage VR, so diode will be acting like a short circuit, and the equivalent circuit is as shown in this figure. Now if you calculate the output voltage, what happens? as the diode is short circuited, you find the output voltage fixed at reference level VR. So V naught becomes VR. So in this fashion, so this shunt clipper which is clipping above reference level actually works. And in the examination point of view, if you have been asked about this question, we need to elaborate the concept of clipper with the help of a transfer characteristics diagram, so which is available in the next slide. So like this. So this diagram has to be drawn to give much explanation about the circuit. So now let us see how this diagram is actually drawn. Now, so initially you just draw this axis which represents a transfer characteristics of the circuit actually, and at the bottom side we used to draw the input signal what we are going to apply to the circuit. Means this is the input signal I am applying, and at the right hand side I will draw the output. So and I did not draw this transfer characteristics. I have just drawn this axis. So in this way, first we just draw the outer view of this characteristics, and since I am applying a reference level VR, so VR is something at above which you want to clip. So this VR is actually pointed first like this. Now, so with the condition, so when the diode is actually on, what happens, the output signal will be actually equals to VR. Means when V naught equals to Vi, the slope of the transfer characteristics will be 1 like this. It is very linear. And if diode is off in shunt clippers, the slope will be 0. Means if the slope is 0, you just draw a straight line like this. And for the slope where V naught equals to Vi, so we need to draw a linear line. Here what happens, except for Vi greater than VR, so rest of all the case the output is actually equals to input. So we get an entire linear line up to the negative peak of the input signal. So let me explain or draw one more time on the empty sheet. So first of all draw this reference axis, and towards the right leave some space and leave the space for output signal, and at the underneath of this reference axis, so draw the input signal what we are going to apply in this direction, and so point out the reference level and the negative peaks. So you need to point out this, so positive as well as a negative peaks of the signal with the dotted lines, and you have to give the reference level also with the dotted lines to be extended in the vertical direction. And now, so based on the operation of the circuit, so when the diode is on, so V naught equals to VR, means there won't be any input signal getting passed at the output side, so the slope will be 0. You just identify, so when Vi is greater than VR, means when input signal Vi what we have drawn here, if it is greater than VR, so what happens, the output is actually VR, means the slope at this instant is 0. You just draw a straight line and indicate slope equals to 0. And similarly, when the diode is on, what is happening, actually that part is actually getting clipped off. The same indication here it is given, the diode D is on. This is the region where the signal is getting clipped off. and when Vi is less than Vr, so when Vi is when Vi is less than Vr, what happens? When the input signal is less than this reference level, the diode is actually in off condition. When the diode is in off condition, we used to get the entire input signal across the output terminal, means V0 becomes equals to Vi, means the slope at this during this entire duration when V0 equals to Vi is 1, means you just draw a linear line up to which the signal V0 is equals to Vi. So in this way, so this is the region where the input signal is getting transmitted towards the output side when diode D is off. So in the same way, so the output signal, after drawing this, this is the output signal. When the slope is 0, you just draw a straight line, and when the slope equals to 1, you just draw the input signal as it is. So this is how the transfer characteristics of the clipper circuit to be drawn, and which gives a better explanation in the diagram itself. So this is about a shunt clipper and clipping above the reference level. So let us see one more circuit, which is the clipper, shunt clipper, which clips the signal below the reference level. So this is the circuit. So let us explain. Let us see how this circuit actually works. So we need to understand the two cases, when this diode is actually on and when this diode is actually off. So what happens here? So when Vi input signal, means the input signal at this point, if it is less than Vr, means if the input signal Vi is less than this Vr, what happens? The diode D gets turned on and it is in forward bias condition. So for Vi, let us see, let us draw the output signal also here, and let us take, this is the input signal what I have applied, and to this input signal, when Vi is the reference level is pointed at this point, I am taking Vr here, and when input signal is less than the reference level, so what is happening here? If the input signal is less than the reference level, diode is getting turned on, and what we get is the output will be maintained at a constant level called Vr. For Vi less than Vr, the output signal is Vr, means this is actually input signal, and what we are about to draw, this is V0. For Vi less than this Vr level, we are getting a value of Vr, and when this Vi value is exceeds the value of Vr, when Vi is greater than Vr, what happens? So when this terminal is having more voltage than this, the diode will be in off condition. When diode is in off condition, it acts like open circuit and the entire input appears across the output. Then for voltage, for the voltage, if Vi is greater than Vr, V0 equals to Vi. Small correction in this, right? So when Vi is less than Vr, output equals to Vr. When Vi is greater than Vr, V0 equals to Vi. Again at this point, again Vi input signal falls below the Vr, means it has to maintain a constant value like this. Again when Vi exceeds Vr, again V0 becomes Vi. In this way, so the signal actually clips the part of the signal below the reference level Vr. Now let us see in terms of circuit operation also. See, so for Vi less than Vr, diode D will be in on condition. So we know the circuit looks like this as shown in figure C, and V0 will be equals to VR. And in the last circuit, if you see, when diode Vi input signal Vi is greater than VR, diode D is off, and you will get V0 equals to Vi. As I already said, this explanation can be very much better in terms of transfer characteristics. So let us see how to draw the transfer characteristics also for the same circuit. I'll just try to draw in the same screen. You just try to observe. First, what I said is I said to draw the reference axis, and so below that the signal what we are going to apply, input signal, and to the right hand side of the circuit we are going to draw the output side. Now first let's draw the input signal. This is the signal what we are going to apply, and as I said, so we need to extend the both positive and negative peak lines with the help of dots like this. And the reference level VR, here it is a positive reference level, so let us say this is the reference level, and this reference level should also be pointed out with the help of dotted lines, and this is actually output signal V0. Now observing the condition here, so let us say first, if so here I am just drawing the input signal in terms of dotted lines so that we can draw the output. So when Vi is less than VR, means when the input signal Vi is less than VR, the diode is in on condition. When the diode is in on condition, we get the output V0 equals to VR. So for the reference voltage, so VR, so let us say this is so here we are pointing this VR. So if the input signal is less than this VR, means at this instant during this time the input signal falls below VR. So at that time what happens, the output signal is actually maintained as a constant value called VR. Since this works as a short circuit in forward bias, V0 becomes VR, means so here the slope is actually drawn as 0. For what? For the signal Vi less than VR, means so except this duration the slope is actually 0. And during this duration what? So when the signal is actually, when Vi is greater than VR, diode is off and the output becomes input, means during this point only we used to get the output signal. Rest of all the case means here only we are getting the slope equals to 1 here, and here the slope equals to 0. So and this is called clipping region, which part has been clipped when the diode D is on condition, and this is a region where actually clipping is not happened. This is diode D equals to off region. So in the same way we need to draw the transfer characteristics. The same is explained in the next slide in this way. So the part where the signal is actually transmitted is given a slope 1, and the part where the signal is not getting transmitted given a slope 0. And this is about shunt clippers, means in both positive clipping above reference level and clipping below a reference level.